All right, you guys, here we go. So we are entering a new unit. We're looking at randomness, probability, and simulation. We've already done this activity, flipping coins without getting sore, exploring long-term regularity. And the big takeaway from that is that chance behavior is really unpredictable in the short run. We see some natural variation in the short run, but has a regular predictable pattern in the long run. So that is so important. I'm going to highlight that takeaway right there. So when we talk about probabilities, could be decimal, could be fraction, could be percentage. We're looking at the likelihood of any outcome of a chance process, and it's always between 0 and 1 that describes the proportion of times the outcome would occur in a very large number of repetitions. So again, really trying to focus on what happens in the long run. This is what we would expect to see. So an outcome of 0 is one that would never occur, and an outcome of 1 is one that would always occur. We are usually somewhere in between those two extremes. So again, 0, no chance at all for it to play out, and 1 means it's absolutely guaranteed to play out. All right, next we're introduced to this concept, the law of large numbers. So if we observe more and more repetitions of any chance process, the proportion of times that a specific outcome occurs approaches its true probability. Things even out in the long run. So here, if I take us back to our coin flipping activity, we saw variation in the short run, but in the long run, most of us saw that we were approaching that true probability, that true proportion of about 50% heads, right? So here we see variation in the short run. But then we approach that true theoretical probability, that 50% heads, once we've accumulated a lot of data, we've run a lot of trials. So we end up approaching our true probability. We'll call that theoretical pretty soon in the long run. Okay, so lots of variation. We expect that with small sets of data in the short run, but we start to approach that true probability in the long run, just like we saw with our coin flips, right? We start to approach that true 50% heads right after we have a lot of data. So then example 1 feels pretty intuitive. According to the Book of Odds, the probability that a randomly selected U.S. adult believes the government staged or faked the Apollo moon landing in July of 1969 is 0.06 or 6%, right? So what is that 0.06? What does that actually mean, right? We're saying, well, this is the figure that we would expect if we took many large samples, right? So we're expecting to see about 6% of individuals who believe that the government staged or faked the Apollo moon landing after we have accumulated a lot of data. So we'd expect this figure if we took many large samples. Okay, so only if we had a lot of data, this is the figure that we would expect to play out, that 6% of U.S. adults believe that the government staged or faked the Apollo moon landing. So again, big takeaway, lots of data, many large samples. So then for B, does this probability say that if we pick 100 U.S. adults at random, exactly 6 of them believe the government staged or faked the Apollo moon landing? Right? We're going to have to say no, that's not what it means, right? It's really describing what we expect in the long run after we gather lots of data. We expect to see variation within our samples. Okay, so again, variation in samples. Right, we'd expect this figure after we collect lots of data. Okay, so again, there's some natural variation within our samples, right? We might go ask 100 US adults, and we might see that 4 of them think the government staged or faked the moon landing. We might go get another random sample and see this time it's 10 of them, right? So in our smaller samples, there's some natural variation. But if we went out, we gathered a lot of samples, we got a lot of data, we'd expect to see that 6% figure showing up in the long run. The next myth that we see a lot is this myth of short run regularity. So runs seem not random to our intuition, but they're actually quite common. So a really good example of that is when you take a multiple choice test and you see a block of the same letter, like you see 8 A answers in a row. You think, oh, I did something wrong. That can't be right, when actually that is very common. So a good example here would be looking at a multiple choice test. Right, so multiple choice test, it's pretty typical to see runs of the same letter. So typical to see a block of, let's say, A answers. Right? It makes us doubt ourselves, we question ourselves, we think we did something wrong, when actually that is pretty common. Okay, example 2, here, one of the sequences below is the result of actual flips of a coin. The other one is faked. It's by a student who's trying to avoid doing the actual flips. Which sequence do you think is the real one and why? So here again, we're looking at someone just simulating 50 coin flips. So in the first one, what we're seeing a lot of alternating and shorter runs. So all that means when we say a run, like a run of 2, means we're seeing a block of 2 in a row. So 2 heads in a row. A run of 3 means we would have 3 of the same in a row, just like that. So this first one is showing shorter runs, right? So lots of alternating, lots of short runs of 2 in a row, a few 3 in a rows, very few 4 in a rows, and then nothing after that. Whereas looking down at B, we see that we have some longer runs here. So here we're seeing 1, 5 in a row, one where there's 7 in a row, and that's right here. So if we're trying to say which one do we think is faked versus real, well, the one that has longer runs, right, that's more common. That's the one that we would anticipate as being real. So this one right here, I'm going to say, I think this one is the one that's being faked because I see more shorter runs, more times where we are just alternating heads to tails, versus this one where we see that big old block of 7 in a row. So a little note here, right, longer runs are common. Okay, we see that in truly random behavior. Okay, next here we have a player is playing the game of craps, needs to roll a sum of 8 on 2 third dice to win the game. The player then rolls a sum of 6, a sum of 7, 10, 10, and 6 on the next 5 consecutive rolls. A spectator yells, "You're due for a win." Explain why the spectator is wrong. So the spectator is assuming that things are going to just finally balance out and we're going to see a sum of 8. But that's not really what actually plays out. What he's really talking about is this idea of the law of averages. Okay, we don't see that outcomes truly balance out or even out if we're only looking at a small set of data. So let's say outcomes will not even out within a small sample. Right? You're not due for anything, but in the long run, we should see that our rolls should work out to whatever that theoretical probability is of rolling a sum of 8. So if I look at how I could get to a sum of 8, right, I'm rolling a pair of dice. So I have something showing up on die 1 versus die 2. There's really 36 total options for what could unfold. So if I'm looking specifically at a sum of 8, that could be a 3 paired with a 5. That could be a 5 paired with a 3. That could be a 2 with a 6, 6 with a 2, or a pair of 4s. Right, so there's really 5 ways I can get to a sum of 6. I'm not sorry, sum of 6, 8, sum of 8 out of 36 total options. So I have 5 ways to get to a sum of 8 out of 36 total possibilities for what I could see on my pair of dice. So if I look at that as a percentage, that would mean 13.16% about. That's really my theoretical probability. That's my chance of getting a sum of 8 on any individual roll, and it's really what we'd expect in the long run, right? So we're not ever due for a particular outcome, but this is the true probability that we should see playing out after we've gathered a lot of data. All right, so I'm just going to label this and say this is what we'd expect on any individual roll. Right, the likelihood of getting a sum of 8, right, we would expect that probability to be 13.16%, and really it's what we would expect in the long run. So again, big takeaway, we see a lot of natural variability that plays out in the short run. Chance behavior is unpredictable in the short run, but has a more regular, predictable pattern in the long run. All right, last skill for today is doing a little simulation. So we're going to do a few simulations over these next few days in this unit, and I'm going to walk you through how you do that with a table of random digits and how you do that with your graphing calculators. So if we're looking at a simulation, okay, we're looking at the imitation of chance behavior based on a model that accurately reflects the simulation. So I'm giving you this first model. We're looking at a basketball scenario. So in an attempt to increase sales, a cereal company decides to offer a promotion. Each box of cereal will contain a collectible card featuring one of these NBA superstars. So we've got Steph Curry, LeBron James, Kevin Durant, James Harden, or Klay Thompson. The company claims that each of the 5 cards is equally likely to appear in any box of cereal. An NBA fan decides to keep buying boxes of cereal until she has all 5 cards. Use a simulation with 10 trials to simulate the random outcomes. Calculate the average number of boxes that need to be purchased to collect all 5 cards. Okay, so our table of random digits uses digits 0 through 9. And we have 5 NBA players, right? We have 5 players. So if we're using all those digits 0 through 9, we need to allocate 2 digits per player. Okay, I've made myself a little chart to the side, which just helps us keep track if we've collected each of those individual player cards. So if I'm giving everyone 2 digits, let's say that Steph is digits 0 and 1, LeBron is 2 and 3, Kevin is 4 and 5, James is 6 and 7, Klay will be 8 and 9. So trial 1, I'm just giving you, let me slide this up, giving you a block of randomly generated digits. So if I look at that first box that's purchased, right? That box is 1. That means we just got Steph Curry. Okay, then 4, we have Kevin. Okay, another 4, we get a duplicate. We want something that's unique. 5, another Kevin. 9, now we have Clay. 2, now we got LeBron. Okay, and then 6, now we have James Harden. So right there, that's where I captured all 5 of them. So over here, I'm just going to look at the total number of boxes it took to get all 5 playing cards. So in this scenario, the first trial, on that 7th purchase, took 7 boxes. That's where I collected all 5 of those players. Okay, trial 2, let's do it again. So here, 3, we just got LeBron. 8, we got Clay. 1 is Steph. 6 and 7, both James. We got some duplicates. So now we're looking for a 4 or a 5. So a 9, 8, there's our 5, right? There's our Kevin Durant card. So that took us 8 boxes to collect all 5 of those player cards, and then we do it again. So for trial 3, right, 7 here, we just got James. 3, we got LeBron. 1 is Steph. Okay, so we got all those guys. 9, we got Clay. 0, we get another Steph. 3, right here, we got LeBron again. 2, LeBron, and then 5, now we got Kevin. Okay, so that took us 8 boxes to get all 5 playing cards. Hopefully you guys get the idea, so I'm just going to tell you what the other ones end up being. This one's going to take us 17 purchases, and then 15, and then 11, 8, 11, 7, and 7, right? So we're just saying how many boxes does it take to collect all 5 playing cards. So then we want to calculate the average number of boxes that need to be purchased to collect all 5 cards. Let me slide this up just a little bit. So I'm looking at my total boxes purchased, right? Really, we saw 99, and we're seeing that in 10 trials. So I'm taking the 99, splitting it by 10, and we get 9.9. So here, based on my trials, and since we have the same blocks of random digits, we should get the same answer. So we should say, well, on average, we're seeing 9.9 cereal boxes need to be purchased to collect all 5 playing cards. Okay, so in this simulation, we should absolutely match because our trials should be exactly the same. We keep purchasing until we've seen all 5 of those playing cards. It just depends on how we've allocated those digits for each player. So if we allocate it the same way, our answer should match perfectly. And again, it's only based on 10 trials, but this is what shook out in this simulation. Okay, we also do simulations with a graphing calculator. It's usually a little bit more efficient, a little easier. So here, if we are using a random calculator, we really just need to use 5 labels, right? We have 5 players, so we need 1 digit for each player. So 5 players. We'll do 1 digit per player. Okay, so here let's say I make Steph 1. I'll make LeBron 2. I'll make Kevin 3. James gets to be 4. And then Klay Thompson, you get to be 5. So I'm using labels 1 through 5. I could have done that differently. I could have used labels 0 through 4. I could have done 2 through 6, but to me it feels easy to do 1 through 5. So then I need to keep buying cereal boxes until all cards are selected. So here our outcomes can be very different. If I'm doing it in my calculator, I'm generating random integers between 1 and 5. And I'm just going to generate one at a time. And I'm just going to keep hitting enter until I've seen all 5 of those digits, right? I want to see the 1, the 2, the 3, the 4, the 5, and think about how long it took me to purchase all of those different player cards. So here I'm in my calculator. I go math over to probability, random integers. I want 1 through 5, and I'm going to generate one label at a time. So in my first trial, I have a 1. I just got Steph Curry. And then I got a 3. I've got Kevin Durant. Next, I get a 2. Let me just copy these onto my paper. So 1, 3, and 2 looking good. Let me hit enter again. I get a 5. So far, so good. I'm just looking for the 4. I'm looking for James Harden. Oh, I just got him. Okay. So that took me 5 boxes. The first 5 boxes, and I got all 5 of them. Okay, so now I'm just going to keep going, right? So I saw it play out in 5 trials. Now I keep going. So I hit enter. The next one would be a 1, another 1. I'm getting duplicates now. Another 1. So I see a 1, 1, 1. We just keep hitting enter. Now a 5, a 3, a 2, a 3, a 5. I need that 4 again. We're going to have everything else. I see a 5. Now I got my 4. Okay. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This time it took me 10 boxes to get all 5 playing cards. Okay, let me do one more trial and then I think you guys get the idea for how it works. So here again, right, that was the last trial where I got the 4. So I'm going to just hit enter, start the next trial. I get a 5, I get a 4, I get a 3. Okay, so next one, 5, 4, 3. Keep hitting enter. I get a 1, and now I'm just waiting for a 2. I got another 3, a 4, a 4, a 1. Got my 2. There we go. Beautiful. So how long did that take me? 1, 2, 3, 4, 5, 6, 7, 8, 9 purchases. Okay. So I would keep going until I've conducted 10 trials. So when I ran this, when I practiced this before, I got some really long runs. I got a 27. I got a 10, I got a 13, a 25, a 9, an 8, and a 7. So in my model, right, this is what I got for those remaining trials. So I'm just using that so I have more data for this example. So now my number of boxes total, let me add those up really fast. I'm going to add the 5, the 10, the 9, that really long run of 27, 10, 13, another long run of 25, 9, 8, and 7, and I get 123. So same idea as before, right? I take that 123, I divide it by 10, and I get 12.3. Okay, so if I write that as a little summary statement, let me just darken that up a little bit, 12.3. Here I would say on average, right, because this is just based on my data, my trials, and we will not match here. Your numbers should not match mine. So on average, I'm seeing that it takes 12.3 cereal boxes purchased to collect all 5 playing cards. Okay, so in these types of simulations, right, we keep going until we've collected all 5 of those playing cards. I modeled for you the first 3 trials and then just pulled the other trial data from when I practiced this on my own. So your data for the table of random digits example, yours should match mine perfectly. We should have different answers when we're running simulations with the graphing calculator. All right, I hope this process makes sense. We'll circle back to it the next time I see you guys. Have a good rest of your day.